Welcome to the deep dive.
Okay.
Today, we're jumping straight into large language models, LLMs.
Right. These things are everywhere now, and they can do some pretty amazing stuff. Reasoning, answering questions.
Really remarkable capabilities. But they're not perfect, are they? There's this key limitation.
Definitely. Their knowledge is frozen in time, basically. It's based purely on the data they were trained on.
Which means they can get things wrong if the world has changed, or even just make stuff up. Hallucinations, they call them.
Exactly. That's a major hurdle. So how do we fix that? Well, the most common way is something called retrieval augmented generation, RAG.
RBRAG. Okay, so what's that about?
Think of it like giving the LLM a library card. It doesn't just rely on its internal memory. It can go fetch external, up-to-date information.
So it looks things up before answering.
Precisely. Early on, people did this with clever prompting, but now there's more focus on fine-tuning the models themselves and scaling these techniques at test time.
Okay, looking things up helps with outdated info. But what about making the LLM smarter about what to look up? Improving the reasoning.
Yeah, that's where things get really interesting lately. Reinforcement learning, RL, is showing a lot of promise there.
RL for enhancing reasoning and specifically information retrieval.
Exactly. There are models like Search R1, Deep Researcher. Some of these even use, actual Google search during training to learn better search strategies.
Training an LLM by letting it use Google. Okay, that sounds powerful, but I sense a but coming.
There's definitely a catch, or, well, a couple of catches. Using real search engines for RL training is problematic.
How so?
Well, first, the results you get back are unpredictable, sometimes useful, sometimes just noise. That makes training tricky.
Right, inconsistent data.
And second, the cost. You need tons of queries for RL training. Someone crunched the numbers like 64,000 queries to Google. That could run you almost $600.
Wow, okay, yeah, that's prohibitive for a lot of researchers. So unpredictable quality and massive API bills.
Exactly. Which brings us to the main topic today, ZeroSearch. This is a new framework from Alibaba.
ZeroSearch. And the key idea here is...
It's a way to use reinforcement learning to make LLMs better at searching, but without using a real search engine during training.
No real search engine. How does that work?
Yeah.
That sounds like it tackles both problems, head-on cost and quality control.
It does. They claim it can slash training costs by something like 88%.
88%. Okay, you have my attention. So how did they pull it off? What's the secret sauce?
The core idea is pretty neat. Instead of a real search engine, ZeroSearch uses another LLM to simulate one.
Okay, an LLM pretending to be Google, sort of.
Sort of, yeah. So you have your main LLM, the policy LLM, that you're trying to train to be good at searching.
Like the student model.
And then you have this other LLM, the simulation LLM, acting as the search engine environment for the student.
And the simulation LLM just provides search results.
Exactly. It takes the queries from the policy LLM and generates simulated documents. Crucially, the simulation LLM's own parameters, its internal settings, are kept fixed while the policy LLM is learning.
So you're only training the policy LLM.
Right. The goal is to get the policy LLM to maximize its reward, basically, answer accuracy, while also making sure its search behavior doesn't drift too far from, like, a standard reference model.
Okay, so you swap out the expensive, unpredictable real search engine for a controlled, simulated one. But how do you make sure that simulation is actually useful for training? How does it learn to act like a search engine?
Good question. That's the first key part. Search simulation tuning. They fine-tune the simulation LLM beforehand.
Fine-tuning it based on what?
They start by collecting real interaction data. They prompt an LLM, maybe a powerful one, to use a real search engine to answer questions.
Okay, so they gather examples of actual search processes.
Exactly. They record the whole trajectory, the queries, the documents retrieved, the final answer. Then they label these trajectories.
How do they label them?
If the final answer was correct, they mark the retrieved documents as positive or useful. If the answer was wrong, the documents get labeled negative, meaning they were noisy or unhelpful.
So they're creating a data set of good and bad search results relative to a question.
Precisely. And then they use these labeled query document pairs to supervise the fine-tuning of the simulation LLM.
So the simulation LLM learns to generate both relevant documents and irrelevant ones.
Yes, that's key. They use some clever prompt engineering, too, tweaking the prompts slightly to signal whether the LLM should generate a useful or a noisy document, including the original question and answer for context.
So after this tuning, the simulation LLM is ready. It can produce both good and bad search results on demand.
Ready for the next stage, which is the curriculum rollout mechanism. This is
Yeah.
where the actual RL training of the policy LLM happens.
Right. The policy LLM generates a query,
Feeds it to the tuned simulation LLM.
which sends back simulated documents. Okay, but where does the curriculum part come in?
Uh-huh. The quality of the simulated documents isn't static. It changes over time. Specifically, it gets worse.
Worse, you mean they intentionally introduce more noise?
Exactly. They gradually increase the proportion of noisy, irrelevant documents that the simulation LLM provides.
Why would they do that?
It's a curriculum learning strategy. The idea is to start easy and get harder. Initially, the policy LLM gets mostly high-quality results, so it can learn the basic mechanics, how to format queries, how to use the search tool.
Learn the ropes when the signal is clear.
Right. Then, as training progresses, the environment gets tougher, more noisy. This forces the policy LLM to become more robust, better at filtering out bad information and refining its search strategy.
That makes a lot of sense. Start simple, then build resilience. How do they control that difficulty increase?
They use a probability function. It dictates the chance of getting a noisy document at any given training step. This probability ramps up over time based on where you are in the training process, from a low initial noise level to a higher final one.
A smooth transition from easy mode to hard mode. Clever.
Mm.
Okay, so the policy model is interacting with this increasingly difficult simulator. How does it know if it's doing well? What's the reward?
The reward is focused squarely on answer accuracy. Did the policy LLM produce the right answer based on the documents it simulatedly retrieved?
Just accuracy.
Initially, they tried simple exact match, EM. Does the generated answer perfectly match the ground truth?
Why?
But that led to reward hacking. The model would sometimes just generate super long answers, hoping the correct snippet was buried in there somewhere.
Okay, not ideal. So what'd they switch to?
They moved to the F1 score. It's a metric that balances precision and recall. Basically, it checks how much of the model's answer overlaps with the correct answer, but also penalizes it for including lots of irrelevant stuff.
So it rewards being correct and concise.
Pretty much. The reward is calculated based on that F1 score. Interestingly, they found they didn't need a separate reward for, making the output look nice or follow a specific format.
The model just learned the format implicitly.
Yeah, it seems learning to maximize the F1 score was enough to encourage well-structured outputs, too.
Okay, F1 score for reward. Now, what about the actual RL algorithms used to train the policy model?
The ZeroSearch framework is pretty flexible. They showed it works well with standard algorithms like PPO, proximal policy optimization,
Right.
and also GRPO, which is group relative policy optimization.
Any difference between them?
Both worked, though GRPO seemed a bit more stable across different models in their tests. But there was another subtle challenge they had to address during training.
What was that?
It relates to how the optimization signal, the gradient, is calculated. Remember, the full interaction includes stuff the policy model generates queries, the final answer, but also stuff generated by the simulator, the documents.
Right. The policy model doesn't control the simulated documents directly.
Exactly. And applying the same learning updates based on both types of tokens could make the training unstable. It's like trying to learn tennis by getting feedback on your opponent's shots, too.
Okay, so how did they handle that?
They use something called loss masking. Essentially, they mask out or ignore the gradients associated with the simulated document tokens during the update step.
So the policy model only learns from its own actions.
Precisely. Only the queries it generated and the final answer it produced contribute to the learning signal. This makes the whole process much more stable.
That makes perfect sense. Okay, we've got the setup. Simulation LLM, curriculum, F1 reward, masked loss. The big question, does it actually work? How did ZeroSearch perform?
The results look really strong, actually, across a whole bunch of question-answering data sets, some similar to what it trained on, others completely new domains.
Like in-domain and out-of-domain tests.
Yeah. ZeroSearch consistently beat the baseline methods. That includes simple prompting, more advanced RAG techniques, and even other RL-tuned models.
Better than other RL methods. What about the ones using real search engines like Search R1?
That was the really striking part. ZeroSearch actually outperformed methods like Search R1 that were trained using real Google search.
Wow. So the simulated environment, maybe because it's more controlled and uses that curriculum, leads to better results than training in the wild, noisy internet.
That seems to be the implication. It's a pretty significant finding.
And was this consistent? Did it work for different kinds of LLMs?
Yes, they tested it across different model families, Quen, Llama, different sizes, from 3 billion up to 14 billion parameters, and also on both base models and instruction-tuned ones.
And it held up.
It held up. The generalizability seems quite good, and as you might expect, they generally saw better performance when using a larger simulation LLM.
A better simulator makes a better student. Makes sense. Did they compare the learning process itself, like how the reward improved over time?
They did. They compared the reward curves for ZeroSearch against Search R1.
Mm.
The overall trend was similar. Both methods showed learning, the reward went up, but the ZeroSearch curve was noticeably smoother, more stable.
Less bumpy.
Right. And eventually, ZeroSearch often climbed higher than Search R1, surpassing it with less fluctuation. They think that curriculum mechanism really helps stabilize things.
So potentially more reliable training. What about the choice of that simulation LLM? How good does it need to be?
That's crucial. They found a fine-tuned 7 billion parameter model could perform comparably to using Google Search as the environment.
A 7B model matching Google? That's impressive.
And a 14B simulation model actually did better than Google in their setup.
Okay, so LLMs can be effective substitutes here. Is fine-tuning essential?
It seems so. The fine-tuned simulators performed much better than just trying to prompt a base LLM to act like a search engine. The fine-tuning likely reduces the gap between simulated and real document characteristics.
And bigger is generally better for the simulator.
Yes, they saw consistent improvement as the simulation LLM size increased. Quality of the teaching environment matters.
Did they look at how the model's search behavior changed during training? Like how many times it decided to search?
Yeah, the interaction turns study. It was interesting. Initially, the number of search turns dropped sharply.
Right.
The model quickly learned the basic format, like I need to call the search tool now, and stopped making redundant calls.
Okay, learning efficiency.
But then the number of turns started to increase again, stabilizing alongside the reward.
So it started searching more again, but this time productively.
Exactly. It suggests the model learned that sometimes multiple, more focused searches are needed to gather enough information to answer complex questions correctly. Even as the reward plateaued, the task was getting harder because of the curriculum, so the model had to keep refining its multi-step search strategy.
Searching smarter, not just more or less. What about those RL algorithms, PPO versus GRPO? Any more insights there?
Well, both worked, which shows the framework isn't tied to one specific algorithm. GRPO might have been slightly more stable,
Okay.
but they also pointed out that GRPO involves repeated rollouts, generating multiple possibilities. Doing that with a real search engine API would get really expensive fast.
So the simulation makes algorithms like GRPO much more feasible economically.
Definitely another plus for the simulation approach.
And do they explicitly test the curriculum? Like what if they did it backwards, hard to easy?
They did. They compared their standard easy to hard curriculum with a reverse hard to easy one.
And the standard way was better.
Consistently better, yes. Starting with cleaner results helps the model grasp the fundamentals before tackling the noise. It supports the whole curriculum learning idea.
Makes intuitive sense. Okay, let's circle back to the cost. They claimed huge savings. Can we put some numbers on that again?
Absolutely. The big one is zero API cost for search engines. That estimate of nearly $600 for 64,000 Google queries. ZeroSearch avoids that completely.
Okay, that's the direct saving, but you still need to run the simulation LLM that needs GPUs.
True, there's compute cost. But they estimated training a 14B simulation model for about 12 hours on 4 A100 GPUs cost around $71.
$71 versus almost $600. That's a massive difference.
It really is. So while you do need the GPU infrastructure, it's often way more cost-effective than paying per query, especially for large-scale RL training.
And potentially more scalable if you have the hardware.
Right. Plus, they suggest you could potentially share one simulation server across multiple different RL training runs, amortizing the cost further. And having different sizes of simulation LLMs available gives flexibility based on your budget and needs.
For anyone trying to push the boundaries in AI research, that cost reduction could be a game changer, making this kind of RL training much more accessible.
It really could democratize this area of research significantly.
Did they give any concrete examples, like show us what the interactions or simulated documents actually look like?
Yes, they had some case studies. They showed interaction trajectories where the policy model nicely followed the think, search, answer format they wanted, even without an explicit reward for it.
So learn the desired behavior.
and examples where it used multiple search terms effectively to find the answer. They also showed side-by-side examples of useful versus noisy documents generated by the simulator.
And you could see the difference.
Oh, yeah. The useful ones clearly contained the necessary info or the direct answer, while the noisy ones were just irrelevant fluff. Seeing that controlled difference really drives home how the curriculum works and why it helps stabilize training.
Okay, so wrapping this up, ZeroSearch seems like a really smart approach. It lets you train LLMs to be better searchers using RL, but without the headache and cost of real search engines.
Right. Zero API cost, better control over the training data via the simulator and curriculum.
Which leads to more stable, effective training.
And the whole thing seems to generalize well across different models and sizes.
It feels like a significant step forward from basic RAG or even RL with real-world APIs. It's a more engineered, controlled learning environment.
That's a good way to put it. The main trade-off, of course, is needing the compute to run the simulator.
Oh, right. You swap API costs for GPU costs.
Yeah.
But as they argued, that often works out much cheaper, especially at scale.
And potentially gives you more consistent results.
Well, this has been a fascinating deep dive into ZeroSearch. It really makes you think about the power of simulation.
Mm-hmm.
If you can effectively simulate a complex, costly, or unpredictable interaction like web search,
Mm-hmm.
what else could this apply to? What other real-world dependencies could we replace with smart simulations to train AI more efficiently and robustly?
That's the big question, isn't it? Could we simulate, say, complex scientific experiments or maybe even intricate social interactions to train AI in those domains without the real-world risks or costs?
Definitely something to chew on. Where else could simulation unlock the next level of AI development? Thanks for exploring that with me today.